Jai Hind everyone. My name is Shan Kumar Singh, B.Tech second year computer science and engineering student from Madan Malvi University of Technology. And this is the second part of my computer organization and architecture assignment. Our today's topic would be introduction to memory organization. We all know that a computer processes a huge amount of data. Now, to manage this data, we use multiple types of memory instead of single memory. In today's lecture, we will be covering the topics related to the memory organization, which are first of all memory hierarchy, levels of memory and their properties, one important level which is cache memory, locality of reference and working of cache memory, and then we will be solving some numericals on cache memory. Right. So let us start from the first topic, which is memory hierarchy. Memory. Now, we have, for example, let us consider our device. We have a laptop or we have a smartphone. We are having a single device. Now, for a layman, it can be considered that he should be having a single storage, but in reality, we don't have single storage. Let me explain it with an example. Consider we have single storage, let's say RAM, to store all the data and programs. But RAM first of all stores temporary memory. If we want to store something permanently, we won't be able to store there. Again, RAM is quite expensive. Its capacity is very much limited. If we take different examples, there might be other drawbacks with different types of memory storages. Therefore, we use multiple types of memory, and each type of memory have its own characteristics. Now, we have a structured arrangement for these different types of memory devices, and that is what we call memory hierarchy. So, a memory hierarchy is the arrangement of different types of memory in a computer system according to their speed, the cost, and capacity. So, let me just write it. Memory hierarchy is the arrangement of different types of memory in a computer system according to different features like speed, cost, and capacity. So let me just make a diagram of this memory hierarchy. Uh, Starting from the top, we have registers, then we have the cache memory, main memory, and then secondary memory. The secondary memory may consist of the hard disk, your SSD, etc. Main memory can consist of RAM, cache memory, and registers. We will be talking in the lecture further. Now, what is the characteristic of this diagram? First of all, secondary memory, we are very well aware about secondary memory. Uh, this is what we usually see when we buy a new laptop or a new mobile phone. Then we come to main memory. We generally never talk about cache memory or registers. However, those who are well known about it always check about them. Now, what do we understand from this diagram? I have made an arrow pointing upwards. It means that this thing is a subset or is actually smaller than the part discussed below. Now, as we move upwards in this hierarchy, the speed of the memory unit increases. The cost per bit also increases, but the memory size is decreasing and the access time is decreasing. Similarly, if we move downwards, the memory becomes larger, but it becomes slower and the cost also decreases. So let me just note it down. as we move upward, first of all, the speed increases. It means that the registers are faster than RAM or the secondary memory. Cost also increases. Memory size decreases. And access time also decreases. If we move downwards, all of these things will be reversed. Right. So now this hierarchy is the reason why we have balance speed, cost and storage capacity amongst the computer. Like we cannot have just registers for fast computing, because registers are if we want the registers worth the size of whatever our secondary memory or hard disk is, then it will be very costly and won't be feasible. So we need to make a balance between these different units. We will be using registers where we need the speed. We will be using hard disks where we need the storage. Right. So now let us know about these units in detail. First of all, we have our registers. Now, as I told earlier, this is the fastest unit of memory. Now, they are located inside the CPU, and they store the data which is currently being processed. Whatever task we are doing currently, the data regarding it is stored within the register. So it is inside CPU and stores the data which is under process. Data which is currently being processed. So what are the characteristics of a register? First of all, it is very fast, small in size, so its capacity is also small, and is used during instruction execution. Instruction execution. Right. Next in the hierarchy, we have our cache memory. Now, cache memory is something which is located between the CPU and the main memory. Like, what do I mean with this? First of all, let me write it. Located between CPU and main memory. What actually is happening, whatever data which is frequently being used, like we are requiring it frequently, they are stored in the cache memory. So it stores frequently used data. Frequently used data. And what is the actually reason we use cache memory is that whatever data we are requiring frequently, we are storing it at a single place, so the access time for that particular data reduces, so that we can perform our instructions faster, we can perform our computations faster, etc. So it reduces our access time. Sorry for the interruption. Right, so we were at cache memory. So cache is smaller than RAM, but it is quite faster. So cache is smaller than RAM, but quite faster. Now I have explained why we are using cache memory. Next we have RAM. RAM, which is also called our main memory, and we are quite well aware about it. RAM, which stands for random access memory, is used to store the currently running program and the active data. It is used to store currently running program and active data. Now what actually happens is that the programs which we want to use are first loaded within our secondary memory. From there, from secondary memory, when we want it to execute, just before the execution it gets loaded in the random access memory or in the main memory. Okay. So last in the hierarchy we have secondary memory. Secondary memory is the place where most of our data is permanently stored. What are the characteristics of a secondary memory? First of all, it has a very large capacity. Everything is permanently stored here, so it has large capacity. But again, since it has large capacity, the access time decreases quite a lot. So it is slower, slower than all of what we have discussed above. It is slower than used for permanent storages. Used for permanent storage. Example written earlier also. I'm writing again. It consists of hard disk, SSD, the magnetic tapes, not very frequent for us. Yes, so till now we have discussed about memory hierarchy. Now let us memory hierarchy and the levels. Now let us discuss about the properties of memory hierarchy. Our next topic is properties of memory hierarchy. Now, first of all, the first property is the inclusion property. Inclusion property states that the data present in the higher level memory must also exist in the lower level memory. It means that if some chunk of data is present in register, it must always be present in the cache memory, in the main memory, as well as in the secondary memory. However, it is not required that some data which is present in main memory, for example, should be present in cache memory. It may be present there, may not be present there. But if we are at a higher level, then that chunk of data, that piece of data must always be present in that lower level as well. So let me write that inclusion property states that data present in the higher level memory must also exist in lower level memory. As explained the example also, let us discuss what is the purpose for this thing. Now, what was happening is that if we require to perform execution over some data which is currently stored in secondary memory, we called it in the main memory, in the cache memory, in the register. If we make some changes in the register and the thing is not present in the lower level of the memory, then after that execution is completed, the data would be lost. Right. So yes, what happens is that it ensures that easier data tracking, also maintains the hierarchy's consistency, and further simplifies our cache management. So first, ensures easier data tracking, then maintains the hierarchy's consistency, and thus simplifies cache management. In this way, no data is lost, and whatever execution is required to be done is executed properly. A second property of memory hierarchy is the coherence property. Coherence property. Now, coherence property states that if data value is updated in one location, all other copies must also be updated. As I said earlier, for example, we are executing some data in the register, some computation is being done, the data is updated. Now it is updated here in the register, but if it is not updated in the lower level of the memory, then if we would be executing some computation on that same data and calling it again, then we will be getting a wrong value. So it is always required that if some data is updated at the upper level of the memory, then it must always be updated at the lower level of the memory as well, at all the levels where its copy exists. So states that if data value is updated in one location, all other copies must also be updated. Like the example is a bit discussed there as well. So what uh, what we can say in a simple term is that we are trying to ensure data consistency wherever the copy of that particular memory exists. So we are ensuring the consistency of the data. So now let us discuss another important topic, which is cache memory in detail. We have earlier known what is a cache memory. Now let us understand it in detail. Let me take an example. I have a library where I have multiple books, but I am studying a course and therefore I require typical books with me every time. So I take those books and put it in the racks in my study table. So now I can easily access those books from my study table, whereas all other books are kept in the library. This is the same logic which we use with the cache memory. If we are frequently using some data, we have been storing it in cache memory so that the access time reduces and we can easily access those data. So first of all, the definition of cache memory. Cache memory is a high speed memory placed between the CPU and the main memory. It's a high speed memory placed between CPU and main memory. Purpose, as I told earlier, first of all, to reduce the access time. Second, it bridges the gap between the CPU and the RAM. It provides a bridge between the CPU and RAM. Characteristics which we have discussed earlier as well. I will just note it down simply. Small in size, very fast, volatile, it's not permanent, and most important, it stores frequently used data. Frequently used data. Now, in within cache, there are different levels of cache. What are those levels? The levels are, we can say, divided on the basis of the speed and the size. So, level of cache on the basis of speed as well as size. We have the first level, second level, and the third level. Now, as the name suggests, the first level would have the fastest speed, and since it has the fastest speed, therefore it must be having the smallest size because it is easier to find things in smaller places. The L2 level is something having a medium speed, and the size is larger in comparison to the L1 level. Similarly, the L3 level would be having the slowest speed amongst the cache. It is again still faster than typical RAMs, but smallest or slowest speed amongst the cache and the largest size as well. So these were the levels of cache. Sorry, it was not visible. Yes. L1 fastest speed, smallest size. L2 having medium speed because it has a larger size than the L1 level, and L3 which is slowest among the cache but it has the largest size. Now this cache memory, it works on the basis of some locality of reference. Like programs tend to, we can say, access some data repeatedly. Now this basis of locality, it can be divided majorly in two types. So next topic, which is locality of reference, can be divided into two types. First is temporal locality, and let us just understand it with an example. Consider a basic for loop. For int I equal to 1 to I less than equal to 10, I plus plus. What is happening here is that the variable named I is been constantly exist. Now this is what we mean by the temporal locality. Like this variable, if it has been exist once, it is supposed that it can be accessed again. What is happening is that I is equal to 1, then we have been incrementing its value, it's going to I equal to 2. That same variable has been called again and again and again. So if a data item is accessed once, it is likely to be called again. Likely to be called again. This is what we mean by temporal locality. Now, here we were referring to single data item, but it is also possible that if a typical memory location has been accessed, then we might be requiring the neighboring data items as well, the neighboring location as well. This is what we call the spatial locality. Spatial locality. A basic example for this would be consider an array. If we have an array and we have accessed the 0th element on the very first element at the 0 index of that array, then we might be accessing the neighboring elements, which is R1 or the element at index 2, etc. So what spatial locality says, it says that if a memory location is accessed once, then the nearby locations are likely to be accessed. Likely to be accessed. Now, since we are all from computer science background and we all know this is a quite a good example in an array. If the locations are adjacent, we might be requiring to access all the elements of the array very soon if we are accessing one element. Right, so this was locality of reference, which was divided into two types, temporal as well as the spatial locality. Now, let us have a hierarchy or the working of the cache memory. Like we have discussed that there are three levels within the cache memory as well: level 1, level 2, level 3. What happens is the CPU is getting the data from the level 1 of the cache, which is getting from level 2, which is getting it from level 3, and the level 3 gets from the next level of the memory hierarchy, which is the main memory. Right, so let us start our next topic, which is working of cache memory. And first of all, make this diagram. Like when CPU needs data, how does it access it? when CPU needs data, CPU asks from the level 1, which further asks from level 2 of the cache. Following this hierarchy, we get from the main memory, which we are taking an example of RAM. Right, so this is whenever CPU requires the data. Now, when a data is found in the cache at whichever level, this is what we call a cache hit. So a cache hit is something when data is found in the cache. Similarly, if data is not found in the cache, it is called cache miss. So we have two very simple definitions with us: cache hit when data is found in the cache, data found in cache, and cache miss when data is not found in the cache. Now, what happens in the case of cache miss is that since data is not found in the cache, then we would be moving to the next level of the memory hierarchy to find that data. So now the CPU will be fetching data from the main memory, and we all know we will be following that hierarchy so that the copy of the data would now be stored in the cache for future use. Now, how is the data transfer happening? Between the CPU and the cache, the data transfer generally occurs in words, while in the cache and the main memories, the data is transferred within the blocks. So now let us see some more definitions regarding cache performance. First of all, what is cache performance? This is something which is defined by some of the parameters which we would be discussing and we have been discussing. The first is of course the cache hit at whenever the data requested is found in the cache, it is called cache hit. Another is cache miss, like we are looking for the data but the data is not found in the cache. From here we get a definition of hit ratio. uh, Hit ratio, as the name suggests, it is the ratio of how many times we have achieved success by how many times we have tried to look for the data. So simple number of hits upon total number of times we have tried. So total memory accesses. Now, from here we can easily define a miss ratio. It would mean number of misses upon total number of time we have tried. So total memory accesses. Also, there is only two probabilities. Either it would be a hit or it would be a miss. So hit ratio can also be written as 1 minus miss ratio. Similarly, miss ratio would be equal to 1 minus hit ratio. Right, so we are having four formulas with us, and from here we get our average memory access time, which is a very important formula. Average memory access time, or the average access time. The average access time is equal to the hit ratio into hit time plus the miss ratio into miss time. Ratio into miss time. The hit time and the miss time depends on the system, how we are accessing the data, and within the numericals we are already given. Hit ratio and miss ratio can be calculated from each other. So with this formula we would be calculating the efficiency of the cache memory. Now Since we have discussed the definitions, let us now look for some of the numericals on the basis of these definitions as well as the formulas. Right. So here we are with the numericals. First, we have a basic numerical where we are required to find the average access time, and we have been given the cache miss time, which is 50 nanoseconds, the hit time, which is 10 nanoseconds, and the hit ratio 80%. Now we are not taking the percentage, but we would be taking it as a ratio. So 80% would be converted into 0.8. Now, first of all, what was the formula for average access time? It was the hit ratio into hit time plus miss ratio into miss time. Yeah, we are having our hit ratio, we are also having hit time, we are having our miss time as well, but we are not having miss ratio. So first of all, we would be requiring to calculate our miss ratio, and from the formula discussed earlier, miss ratio is nothing but whenever there is no hit, there is a miss. So we would be minusing it from the hit from 1. The hit ratio would be minus from 1. So we would get the miss ratio as 0.2. Now we can calculate our average access time. Putting the values in the formula, 0.8 into hit time as 10 nanoseconds, 0.2 to hit time as 50 nanoseconds. Here we get 8.0 plus 10.0 nanoseconds. Overall, 18 nanoseconds. This is our answer. Next question. In this question, we are required to find hit ratio. What we are given is that first of all, our average access time, which is 120 nanoseconds. We have given two terms, namely main memory access time as well as the cache access time. Now, this is nothing but wordplay. What main memory access time means is that whenever there is a miss, we would not be finding our data in the cache, and we would be requiring to look for the data in our main memory. So whatever time required would be the access time of the main memory. So main memory access time means nothing but our miss time. Similarly, the cache access time means nothing but our hit time. Again, we have our formula. AAT is equal to hit ratio into hit time plus miss ratio into miss time. We have our average access time, we have our hit time, we have our miss time as well. We are required to find our hit ratio. Now here we are having two variables. Now let us consider the hit ratio as h. So from the formula, we would be getting our miss ratio as 1 minus h. And putting these values in the formula, we have the average access time as 120 is equal to hit time, which is 100 nanoseconds, into h plus the miss time, which is 200, 1 minus h. So it is 100 times h plus 1200 minus 1200 times h, 20. 120 is equal to minus 1100 times h plus 1200. Putting it this side of the equals to, you're getting h is equal to 1080 by 1100, which is somewhat equal to 60 by 50. Now we can calculate it with the help of a calculator, but the hit ratio would be 59 by 60. In percentage, it would be something around 97 or 98%. So which is right at 98%. Similarly, the miss ratio, which is 1 minus h, would be 1 by 60, or something close to 2%, 1 or 2%. Right. So this was all from the second part of the assignment. We have discussed the different parts of the memory organization, memory hierarchy, the levels of the memory hierarchy, the properties, and then we have discussed in detail about the cache memory, locality of reference, how does the cache memory works, some definitions as well as the formulas from the cache memory, and lastly we have completed with our numericals. This was Shan Kumar Singh, roll number 20240211065. Thank you very much.